Hello everyone. I am Koushal, a second year undergraduate student in the Department of Electrical Engineering. Today I will be giving the seminar on history of OpAmps. Firstly, before I start the presentation, I would like to thank my guide Professor Deleep for giving me the relevant material for the seminar and guiding me through this course. Let us now start this seminar on history of OpAmps. So firstly we'll go through the flow of the seminar. So first I'll discuss what an op-amp is and how it works. We'll see the functionality and the internal circuit of the op-amp. We will see what uses an op-amp has and some of its characteristics. We'll also see how how an op-amp component found in the market looks like. Secondly, I'll discuss all the applications of op-amps in our daily life. We will see how ubiquitous it is and how it is present in a wide range of electronics. We'll see the wide range of applications it has in almost every field. Then we'll move on to how and why the op-amp was discovered, what was the motivation for inventing the op-amp, and how it was used in its early days. Then we'll see the timeline of the development of op-amp and how it was developed through the decades. When it was first made, when it was first made commercially available, and when it started being made using solid-state devices, and how it became an integrated circuit. We'll look into all of this. Finally, we'll see the life of Bob Whitler, who was a genius and a legendary hardware designer who single-handedly started the whole unlocked integrated circuit industry. He was a pioneer of analog IC design. He was a very creative individual and kind of mysterious. We'll see what kind of major inventions and discoveries he made and how it impacts the world today. So, firstly, what is an op-amp? Op-amp is basically a very high-gain electronic voltage amplifier with differential inputs and a single-ended output. So the meaning of differential inputs is that, as you can see on the right side picture here, there is a plus terminal and minus terminal. So with these differential inputs, uh, uh, so input is provided through these differential inputs and it has a single output terminal. The op-amp is short for operational amplifier. It can So the op-amp can be used to perform many arithmetic operations like addition, multiplication, integration, and differentiation. Uh, so uh, uh, the name operational amplifier comes from this only. So we know that it's a amplifier, and the term operational comes from the fact that it can perform all these kind of arithmetic operations. And uh, the op-amp uh, the op-amp output voltage is uh, a V out, as you can see in the figure here, is some large gain, which is typically 60,000 to 1 lakh times the input voltage difference, which is V plus minus V minus. And the op amp output is basically the high gain times the difference between this input voltage. And it has two input terminals. One is the plus terminal and the minus terminal. The plus terminal is called the non-inverting terminal, and the negative terminal is called the inverting terminal. So in addition to this input and output terminals, we also have two other input pins which supply power to the op-amp IC. These supply power to the MOSFETs or transistors inside this op-amp. So this op-amp is generally used in negative feedback configuration. So there are many uses of using it in negative feedback configuration, such as a precise gain can be achieved, and it depends on the elements connected outside of the op-amp and not on the op-amp itself. And this gain can remain independent of temperature variations, and it because of this negative feedback, the bandwidth of the circuit is increased and the non-linearity of the circuit is decreased. And as you can see on the right here, this is a typical component which you will find in the typical op-amp which you will find in the market. So let us now move on to the applications of op-amp. So it is no exaggeration to say that op-amps are found in almost all electronic systems around us. They can be found in any application. You take any device and there is an op-amp inside it. So these are some of the many applications in which an op-amp is used. So op-amp is an amplifier, so it can be used as any type of amplifier. There are many amplifiers out there, low noise amplifier, power amplifier, and many such. And it is used in sensor circuits in sensors such as ultrasonic sensors, photo detectors, and many other sensors. And it is used in control applications and signal processing applications, such as a filter for filtering out, such as a low pass filter for filtering out high frequency noise, band pass filter, high pass filter, and many such things. And it's also used in ADC DAC data converters, which are integral components in communication circuits. Like the whole communication uh, today depends on these ADC and DAC data converters. Uh, Occasionally, the op amp is also used in positive feedback. When when it is used in positive feedback, it operates as an oscillator or trigger. One such example, and waveform generators like the ramp generator or the square wave generator. One example of a trigger is a Smith trigger. It is used in active filters, as I mentioned before, like a low pass filter or high pass filter, and it's also used as an active rectifier. It is used in voltage and current regulators, comparators, peak detectors. So you can see ADC here on the right side, which is called the SAR ADC, Successive Approximation Resistor ADC. And you can see that the op amp is used as a comparator here in the middle. Uh, so a comparator is basically like it compares the two voltages here between the plus and the minus terminal, and it outputs a bit, a 1 or 0, uh, depending on which input is higher. So if plus input is higher, it will output a bit 1, and if plus input is lower, it would output a bit 0. And this is one of the most commonly used ADC. It has high precision, it has low IC surface area, so it's very commonly used in communication circuits as a ADC. And one more application is, as I talked before about the filters. This is a Tau Thomas biquad filter, as you can see the circuit here. And this filter, by slightly changing the resistors or capacitors, you can achieve any kind of output, uh, any kind of filtered output, like a band pass output, low pass output, high pass output, notch output. So this circuit can be used to build any type of filter. So as you can see that the op amp has many applications, uh, and it's very important for an electrical engineer to understand how an op amp works. So now we'll move on to the early development of the op amp, uh, how it was used and how it was developed using vacuum tubes. So the first critical invention in the development of the op amp three the three-element triode vacuum tube called the Audion, invented by Lee Forrest in 1906. An enabling invention for this triode vacuum tube was the diode vacuum tube which was invented by Fleming in 1904, which was called the Fleming diode. Based on that design, Lee Forrest uh, designed this three-element triode vacuum tube, and this uh, as you can see the triode Audion vacuum tube here, and it has three terminals: the filament, the grid, and the plate. So the filament terminal is of this picture is on the left side, and the grid and plate terminal are on the right side. As you can see, there is a small grid in the middle, which is the controlling terminal. With the help of this terminal, you can control the flow of electrons between the filament and the plate. Uh, Thereby, you can achieve signal amplification by applying a potential to the uh, grid terminal. So this was the first device capable of signal amplification, and yeah, as I told before, this was achieved by the grid terminal placed between the filament and the plate. And this Audion vacuum tube was widely used in radio receivers and transmitters. So another enabling discovery in the development of the op amp was the development of the negative feedback principle by Harold Black at Bell Laboratories. So This so they developed a theory based on a general high-purpose amplifier, and they saw that it has many applications. If we had such a device, they could achieve many things, and uh, it can be used for many applications. So this created a desire for developing a general purpose high gain amplifier. So these two discoveries were the major discoveries enabling the development of the op amp. And after that, uh, vacuum tube based op amps were used in analog computers. In, so in the 1940s, op amps were made using uh, vacuum tubes, and they were used in analog computers to simulate differential equations. And uh, uh, so as they can be used to simulate differential equations, they were used to trace out the trajectory of an aircraft. So these op-amp based analog computers were very widely used in weaponry in the World War II. So they were used in artillery and radar systems, which generated a hit rate of 90%, which was ridiculously high number for a missile at that time. So yeah, so now we'll see the timeline of the development of op-amp after the vacuum tube era, how it evolved. So first in 1941, the op-amp was first encountered in a patent for the summing amplifier. It was filed by Carl of Bell Labs, and it was made using three vacuum tubes. And it had a single inverting input and no non-inverting terminal. Actually, in this paper, Carl never mentioned the name op-amp in his paper of the summing amplifier. It was achieved using the vacuum tube, and uh, the summing amplifier is one of the basic applications of op-amp we see nowadays. So after this, uh, in 1947, an op-amp with explicit non-inverting terminal was found in a paper. So op-amp was first defined and named in this paper by John R. Ragasiri of the Columbia University. So at the end of this paper, a student of Ragasini gave a design for the op-amp which contained the non-inverting terminal. So this paper talks about the applications of op-amp in negative feedback and how it can be used for control applications. So this was the first time an op-amp with a non-inverting terminal was encountered. And then in 1953, the first commercially available vacuum tube op-amp uh, was in 1953 a commercially available vacuum tube op-amp uh, was introduced. So uh, the vacuum tube op-amps were made available by the release of the model Kit 2W by George A. Philbrick, and you can see a picture of it on the right side. The GAP/R just refers to the name of the company, which is George A. Philbrick Researches, and this was a vacuum tube op amp which was first made commercially available. And then in 1961, a solid state discrete IC op amp was introduced. So uh, the birth of the silicon transistor in 1954 by William Shockley and the planar process in 1959 by John Herney made ICs to be commercially useful. So the manufacturing operations became significantly cheaper, and it was ready to be made commercially available. So by 1961, the first solid-state discrete IC op-amps were being produced. And on the right, you can see a picture of the GAPR P45, a solid-state discrete IC op-amp. So this P45 uh, had a gain of 94 dB, uh, and uh, and it was intended to use to deal with signals in the plus or minus 10 volt range. So we'll move to the second half of the development of op-amp. So in 1960, the first monolithic IC op-amp was developed. It was developed. Its name was the MUA 702, and it was developed by Bob Weidler in Fairchild Semiconductor. But they had rushed the production of the MUA 702 before Bob Weidler could uh, uh, clearly define its properties and think about it properly. So it had many issues, like it had very low gain, and it had a very low output driving capability. So after uh, after that, in 1965, the MUS 709, also designed by Bob Weiler, was released. And in this version, Bob Weiler corrected all the mistakes he had done in the previous model. So in 1968, the MUS 741 op-amp was released, and this was one of the most popular op-amp uh, of all times. It is still in manufacturing today, and you can find it in the market. So this was designed by Dave Fullager in Fairchild Semiconductor. So this was similar to the LM101. This LM101 was released in 1967 and was designed by Bob Weidler. He had shifted to a company called National Semiconductor. But this MUA741, it included a 30 picofarad compensation capacitor inside the chip itself instead of requiring external compensation. This compensation is basically we add some elements in the circuit to make the circuit stable and to make it work over a wide range of gains. So, because of the superior manufacturing facilities present at Fairchild Semiconductor, Dave Fullager was able to include this 30 picofarad capacitor inside the chip. And you can see a picture of this op amp on the right, which was the most popular op amp of all time, and you can still find it in the market today. So in 1970, the first high-speed low input correct op amp was uh, made available. This low input current made was enabled using the FETs, which are the field effect transistors, and later in the 1980s, op amps were majorly made using MOSFETs. They replaced FETs, and we were using MOSFETs. So, and one of the most famous, one more famous model is the LM324, which was released in 1972, which was an op amp which came in a quad package, which means that there were four separate op amps in one package, and this became an industry standard. And you can still find such op amps nowadays. So, as you can see here, this is a Texas Instrument LM324 op amp, quad package op amp. So now we'll move on to the life of Bob Weidler, who was genius and a legend. And so Bob Weidler was a fiercely independent individual. He was very happy to be by himself, and he did not care what others thought about him. He did almost everything by himself in a stunning way, uh, so which was natural to him. So he was a legendary hardware designer, and he single-handedly started the whole analog IC industry. Uh, he was more of an artist than an engineer. Like he prioritized uh, the idea of creativity over general intelligence, and his every design had something that was far ahead of the crowd, which made his designs very famous during his time in the 1960s and the 1970s. So now we'll look into into the early life of Bob Weidler. So he was inspired by his father Walter Weidler, and he learned a lot about radios and transistor physics. So his father, Walter Weidler, he worked on radios, and he also worked on a project managed by William Shockley. So Bob Weidler learned a lot from his father, and he became inspired by his father. And one of the first jobs Bob Weidler took up was he joined the Air Force in U.S. Air Force in 1958, where he taught a class on electronic equipment and devices. You can see a young picture of Bob Wheeler here at the age of 16. And an interesting fact is that uh, he was the first baby to be monitored by the wireless radio. So his father had developed the radio, and he was one of the first baby to be developed by to be monitored by the radio. It's just a fun fact. And so yeah, he joined the Air Force and he taught a class on electronic equipment and devices. And when while he was working there, he published a book called Introduction to Semiconductor Devices at an early age of 21 years. and you can see a picture, cover page of the book on the right hand side. So, by seeing this book, we can understand that he had an extraordinary capabilities to simplify complex problems, and he also understood the importance of hard work. Like he used to he used to work hard, and he understood that hard work, with hard work, you can achieve anything. So, after this, later he joined the Ball Brothers Research Corporation, where he designed analog and digital circuits for NASA's orbital station. So while working for this Ball Brothers Research Corporation, he also studied in the University of Colorado. Uh, and while working at Ball Laboratories, he met John Herney and Sheldon Roberts, who were the co-founders of Fairchild Semiconductor. And after seeing them, he got inspired and he decided to work for a semiconductor manufacturing company. And while working at Ball Brothers, he was supposed to work on uh, the evaluation of digital IC components with application in analog circuits. Weidler, however, he considered digital design and digital parts as low class work, which did not need much talent. His argument was famously that uh, every idiot can count up to one, and the real challenge for him was analog design. So, after seeing John Herney and Sheldon Roberts, he quit the Ball Brothers research and he joined the Fail Set Semiconductor, which was co-founded by uh, John Herney and Sheldon Roberts. So here in Fairchild Semiconductor, he met Dave Talbot, who became his best friend, and these two would go on to create create almost all of the components in the analog IC industry in the 1960s and 70s. So they both pushed each other and they worked harder. They kept their work secret and often worked without even the management knowing. Uh, so they both improved manufacturing methods, which reduced the price of the planar process, and which prompted the development of linear ICs. So they did this by secretly running experiments, and they worked. They pushed each other harder. So, so while working here at Fairchild Semiconductor, Weidler, he found about different limitations of working with integrated components as compared to discrete components. So these are some of the parasitics, as you can see here, these 4 points of integrated components. So the first point is that the integrated transistor has parasitic components which are not present in the discrete parts. So as soon as you keep the transistor in the integrated circuit, it it has some parasitic components which will disturb the functionality of the circuit. So and no large value resistor should be used because of its area limitation. And as large value resistors have large areas, and low large value capacitor should be used because of the same area limitation, and no inductor should be used. These are some of the rules he found about designing. Weidler found about designing analog integrated circuits while working at Fairchild Semiconductor, and these are even widely used in the industry today. So, while working here in 1963, he designed the MUA702, the first linear IC operational amplifier. And you can see a picture of him here, like on the right, lecturing about the MUA702 at Fairchild Semiconductor. And later, he designed the MUA709, which was the first widely used monolithic op amp. So we can say that Bob Weidler, he was the first ones to introduce uh, uh, the integrated circuit op amp, and uh, so he was very famous for this invention of this monolithic op amp. And while working at Fairchild Semiconductor, he also patented the Widler current source, uh, which is a way to generate very low currents without using high value resistors, because we can't use high value resistors because of area limitation. So we could generate some very small currents using a transistors and a medium value resistor, and that was basically the Wilder current source. And he also put into production the MUI710 and MUI711 comparators, which had a, a record 40 nanosecond response time, which was unlike any other circuit uh, which was in the industry out there. And we saw the functionality of an comparator before in the SAR ADC. Uh, you can see on the right here, this is a design of the MUI709. Uh, and this was a better design as compared to the MUI702. In the MUI702, uh, Weidler hadn't completed the design yet, and but the management at Fairchild Semiconductor found that this op-amp had huge demand and they rushed production. Hence, he couldn't completely design the MUI702. But in MUI709, he had completely designed it, and it became very popular. So this is a circuit and the integrated circuit layout of the MUI709 op-amp. So later, in Fairchild Semiconductor after 1965, he found out that because of his inventions, uh, the company was getting a lot of money. So he and Dave Talbot, they went to the management and they asked for money, but they didn't give them any. So when Bob Weidler was leaving Fairchild Semiconductor, his boss asked what would keep him from leaving Fairchild, and Bob Weidler replied that uh, he wanted to get $1 million tax free by any which way he wanted. But yeah, they didn't pay him the money, so he quit Fairchild Semiconductor and he joined National Semiconductor. So before joining National Semiconductor, the co-founders there they had given him 20,000 shares of $5 each. So he had become a net worth of $1 million. Uh, and so while working here, Bob Weidler first he concentrated on voltage regulators, and he produced the Analog Industries first voltage regulator, the LM100. And in 1967, he designed the LM101 op-amp. This was an op-amp with improved gain over the MUS709 as we saw before, and it has decreased input current, which was achieved using the FETs. And it had protection against short circuit. So after this 1967, as we saw previously in the timeline before, in 1968, Dave Fullagar and Fairchild Semiconductor released the MUS741 op-amp, which was the one of the most successful op-amp of all times. And yeah, so later Bob Widler he designed the LM101A, which uh, which was functionally similar to the LM101 op-amp, but but uh, he pioneered the use of the FET field effect transistor. So this was the first time a field effect transistor was used in the integrated circuit. So you can see in the picture here that Bob Weiler is holding an axe, and so there is an interesting story about this axe. There are interesting stories. We don't know if it was exaggerated, but this was what I found in the book. Uh, there was a story that he used to keep the axe in his office, and whenever he used to feel frustrated when something was not working, he used to take the axe and he used to go in the woods and he used to cut trees to vent out the frustration. So, and this also helped him in another way that he rented a house which had a fireplace. So he would frequently use the wood he had uh, cut in the forest in his house. And uh, there was another interesting story about this axe that once he got a report of uh, a data sheet of a component, and it had staples on it. So uh, for some reason he couldn't remove the staples on the paper. So he got so angry that he went back to his office. He brought his axe and he broke down the whole table. Um, so these are some of the interesting stories about the axe he was holding in the picture here. So as we move on, in 1969 he devised a new device called a super beta transistor, which was used in the LM108 precision op amp. So the super beta transistor, he was able to achieve this super beta, I mean the high beta, using very low base width of the transistor. So because of the low base width, the breakdown voltage was very low, and it needed so the development of this LM108, it needed uh, a very clever use of circuit design techniques, in which Weidler was a master of. Uh, so these op amps had very high gain and low voltage devices capable of on operating on very low input current. So he devised the super beta transistor with the help of uh, Dave Talbot, whose picture you can see here on the right. And in the late 1960s, he invented the Weidler's band gap voltage reference. Uh, this Weidler's band gap voltage reference is very widely used in voltage regulators and is even widely used in the industry today. So this band gap voltage reference is we need a voltage reference for developing the voltage regulator. So he devised a method in which by uh, uh, seeing the band gap in the material, we could generate a voltage reference. So the band gap, it doesn't change with temperature, and it doesn't change with what current is flowing in the circuit. So it provided a perfect reference voltage uh, to be used in voltage regulators. So using this wireless band gap voltage reference in 1969, uh, he designed the 5 volt linear voltage regulator LM109, and this was the first among the uh, five. This was the first 5 volt linear voltage regulator, and later National Semiconductor, it released Weidler's LM113, the first dedicated two-terminal voltage reference IC, and this LM113 was kind of like the Zener diode, where you reverse bias it and it maintains a constant voltage difference across the two terminals. And in 1917, Bob Weidler and Dave Talbot, uh, they resigned from National Semiconductor when National Semiconductor refused to reward them adequately. So the 20,000 shares which Weidler had, he sold them, and he uh, got some money. He got a huge amount of money, and with that money, he took a vacation for around 3 4 years in Mexico. So this combination of Bob Weiler and David Talbot, so these two single-handedly ran the analog IC industry in the 1960s and 70s. You could also say that they were the Steve Jobs and Bill Gates of the analog IC industry. So Uh, as I said before, Bob Weidler had gone on a vacation for around 3 to 4 years after 1970, after leaving the National Semiconductor. So again in 1974, he returned to National Semiconductor, where he stayed till 1981. And during his time here, he designed some of the revolutionary voltage uh, uh, regulators and amplifiers. And he designed the LM12 power amplifier and the LM10 ultra low voltage amplifier, which were introduced in 1978. So these were so revolutionary that for about 10 years, no one in the analog IC industry was able to produce a circuit that matched the LM10 voltage amplifier. So on the right, we can see Bob Weidler designing the LM10 in National Semiconductor. So after 1981, he again left National Semiconductor, and in Swanson and Hopkins, they co-founded Linear Technology. This is the same company which developed the software LT Spice, which is famously used for circuit simulation. But later he left LT in 1984 over some patent issues with LT products, the LT chips from LT1 to LT20. He, he argued that they used most of his patents and they did not reward him in royalty. Uh, yeah, so he left the case to his lawyer and he left LT in 1984. So after that, he again resigned National Semiconductor in 1984. Uh, he worked as a contractor there for the rest of his life. And in 1991, sadly, he died of an heart attack while jogging up a hill. So this was a man who was a legendary uh, a designer who had the most unique ideas, and uh, he was uh, he was very independent. And so the final conclusion is that Bob Weidler he accomplished an extraordinary amount of life. He achieved an extraordinary amount of work in his short life. Uh, he never accepted anything short of the best, and he worked very hard to generate his design. So Bob Weidler he searched for perfection, and he will live with us forever. So that concludes the seminar, and uh, these are some of the references and further reading. Uh, these are some of the references I referred to while developing this seminar. And you can also refer to these links, and you can also read this book, History of Semiconductor Engineering, as a further reading. Thank you.